Hello, I'm John Seibert, a math and computer science student at Bloomsburg University. In this poster entitled Mapping Integers to the Smallest Description of an Integer Possible in Python, I will discuss how I built a function mapping integers to the smallest integer possible based on a framework of principles using Python. If we're only given a computer program and an input, can we always get an output from the program? After considering this carefully, you cannot be sure you can get an output, and here's the main argument. Suppose a program takes itself as an input, and we have a magic oracle as well that tells us if the program runs forever or halts. If the oracle tells us the program runs forever, the program will halt, and this is also true vice versa. Essentially, the oracle must be contradicted, rendering it a sham. This is Cantor's diagonalization argument, showing no algorithm can correctly answer the question. We will build a function that is actually computable for every single input. Let's pass any number into a function called the cost function. We call m our input and c of m our output, and if two operands a and b sum or multiply to m, then we need to minimize the sum of c of a and c of b. This is easily computable because they're smaller values of the function. As figure 1 explains, for each combination pair, we consider both operation and lower the cost that way. Once we exhaust every combination pair, we go to the next number and we repeat till we hit the limit set by the user. The program halts. I built a framework on 5 basic principles, 3 of which that come from Max Norfolk's 2021 paper, and 2 of which that I came up with for my research. It is also worthy to note that any iteration that we have must have a fixed upper bound. So the driver algorithm explains in figure 2 how does the sub-algorithms change the cost. And we can also see in figure 3 that sub-algorithms can be in any order leading to the same result. Since each number iterated through the driver function has a binary representation, we can use it to define an upper bound. In figure 4, we plot the upper bound in costs against every number passed through the driver algorithm. The blue represents the costs, while the yellow represents the upper bounds. Some numbers only show one color, and this is because of the cost of just using binary. In conclusion, the upper bound of finding the cost of an integer uses solely the binary function. The log base 2 part of the formula represents how many digits we would need in the binary representation. Hence, the upper bound definition just becomes the cost associated with solely binary. Since we increment by just the input, we cannot use subtraction as it relies on cost values higher than numbers passed into the driver function. For future work, other ways to organize the program will need consideration to accommodate sub-algorithms such as subtraction.